In this video, I will discuss the liquid-liquid equilibrium data, and this will be the other key part that we need in addition to material balances in order to solve liquid-liquid equilibrium problems. It comes in the form of a ternary phase diagram. This is what this is called. Ternary having the same root word as triangle because it looks like a triangle because there are three components. And I'll spend some time going over how you read one of these things because it can be somewhat confusing. So ignore this bottom dome for now, and let's just focus on the triangle part of the diagram. Each point within this triangle represents a different composition of three things. So at the vertices of the triangle, I have pure component that it labels. So this is pure acetic acid is at this vertex. Or in other words, 100% acetic acid, 0% water, 0% vinyl acetate. Ditto for the other two. This was the 100% water down here at this vertex, and 100% vinyl acetate is at that vertex. And these numbers on the side are corresponding to lines that are perpendicular to the point. So in other words, this horizontal line corresponds to 90% acetic acid. This horizontal line corresponds to 80% acetic acid, so on and so forth. So by looking at any point within this diagram, I'll just do one for example. Let's say this point right here. It can be confusing to draw lines because there are 6 lines that emanate from this point, and it can be hard to figure out which one you are discussing. So what I like to do is draw my perpendicular lines, right? So this line, this horizontal line that I just drew, is the third line down that is horizontal. And the horizontal ones are going to be perpendicular to acetic acid. So that tells me that this composition is corresponding to 70% acetic acid. And this 30% is not referring to the acetic acid. Instead, this 30% would correspond to the vinyl acetate, but these lines are going to have that shape. So it's going to slope down to the right. Similarly, if I look at this line is going to be perpendicular to the vinyl acetate down here. So that's how I know to look at my vinyl acetate axis. So therefore, this point that I drew is going to be 10% vinyl acetate. And then for any system of 3 components, once I figure out what 2 of them are, the third one is then set by the physical constraint. So in this sense, I could say that the mole fraction of water must be equal to 100 minus 70 minus 10, or in other words, 20. Let's say I forgot that. It is constrained by looking at the 2-dimensional diagram. So the last axis that I have not drawn would be this one. You can see that that corresponds to 20% water. So it's 20%, 30%, 40%, 50. I'm always looking at the directions that the lines are going when I'm reading the composition of these diagrams. So that is how to read these diagrams. I think you learn how to read one of these in your safety class as well. All right, now let's talk about the actual equilibrium data that is written on this plot. This solid curve is called the equilibrium dome. And you can derive what the shape of this is by solving a thermodynamic model. So for this class, this is a topic that's better covered in phase. I didn't quite get to it when I taught phase over the summer, I don't think. But in theory, you would be allowed to derive the shape of this curve by solving a model like the NRTL. So for this class, you'll never need to worry about drawing your own equilibrium diagram from thermodynamic models. I would always give you either the plot, or I would tell you that an experiment was done and this is what the compositions happen to be. So the main point having to do with the equilibrium dome is that all points inside the equilibrium dome are the immiscible region. So this outside the equilibrium dome is the miscible region where all 3 things coexist together. Therefore, I never want to have a composition that is in the miscible region for a liquid-liquid extraction because outside this point, nothing happens. Like I said, it doesn't phase separate. Inside, however, is called the immiscible region, and that's where we have phase equilibrium occurring. Immiscible region. And this is inside phase diagram or phase envelope. These dashed lines inside are called tie lines. And truly, there are infinite number of tie lines, but if you had every tie line drawn, it would quickly become overwhelming. So in practice, only a few of these tie lines are drawn. And if you ever need a tie line, another tie line, you can simply sketch it in just by splitting the difference between the straddling tie lines. So a tie line is important because whenever you have a composition that lies within the immiscible region, let's say we had a composition here, and practice reading what this composition is. So just to yourself, see if you can figure out what the percentage of vinyl acetate, acetic acid, and water is for that point that I just drew in light blue. The answer is that it is 20% acetic acid based on the horizontal line that is perpendicular to the pure acetic acid point up there. It is 30% vinyl acetate based on this line and 50% water based on that line. So that is the composition. So let's say that I fed 50 moles of water, 20 moles of acetic acid, and the other 30 moles of vinyl acetate to a mixer settler, and I mixed it up and I sent it to a settler. The tie line tells you what your equilibrium compositions are going to be out of the settler. So you follow the tie line. The composition cannot exist at this point. It's not thermodynamically stable. Only points on the phase envelope are thermodynamically stable. So you find where the tie line intersects with your phase envelope, and that will become the composition of your two phases. So the phase that is closer to your water, if water were the diluent, this would be your raffinate. And this can change, by the way. The only thing that's constant is the thing that is across from the phase envelope is your solute. But what is the diluent and what is the solvent can change based on what is the original diluting thing and what is the thing that you are adding. So in this case, let's just say that water is the original diluent. This would be the raffinate. Again, it does not have to be this way. You can flip that. This would be 70% water, 22% acetic acid. Again, you have the problem of being precise off this graph is rather tricky. And the other 8% would be vinyl acetate. At the other end is my extract phase. And you could also read the composition off that. 15% acetic acid, 82% vinyl acetate, and the other 7% then would be left to water. Okay, they must add up to 100. So typically what I do is I just do the first two reading off the graph, and then I say 100 minus those other two, and then just do a quick check to make sure that it works. So from that will tell you what your resulting compositions will be. That's going to do it for this video. In the next video, which will be in the next class period, I'll show you how you put all this stuff together in order to solve a single stage liquid-liquid extraction problem. See you in the next video.